Good morning, good afternoon, good evening, wherever you are in the world. Welcome to my show. My name is Diana Hooper, and I'm a postdoctoral researcher at the University of Helsinki. First time I'm actually saying it like that in my introduction. I'm a postdoctoral researcher at the University of Helsinki. My speciality is cosmology. So that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts. Hey, Scott, great to see you in first today. Thank you for being here so regularly, as always. So yeah, I study everything inside the universe and all of the cool phenomena happening inside. So it's a great topic. And I love talking about what I do. I love talking about cosmology. I love talking about the universe. I love jumping on Happs here and talking to everybody about the cosmos, about the wonders of the universe, about all of the cool things happening inside the universe. Hey, Gabriella, nice to see you. Thank you for joining. I just got distracted by a message, realized it wasn't important, so now I've muted my phone. Sorry about that. Most regular thing about me, apparently. Well, I appreciate you being here, Scott. It's always nice to see you, and I do appreciate your puns and jokes. So yeah, I love coming here on Happs and talking about space and the universe and everything happening inside the universe. Hey, Anne, it's great to see you. Glad you could make it. Thanks for joining. So I've been a bit absent on Happs the last month or so because I've been moving country. I was in Belgium. Well, technically I was working in Belgium. I was living half in Belgium, half in Germany with my partner. And I've managed to move everything up to Helsinki. So I'm now in Finland. Started my new job actually on Friday at the University of Helsinki. So a new job, new country, trying to learn a new language, lots of changes. So it's good to go back to my routine of coming on Happs on a Sunday to tell you all about the wonders of the universe. So I do have a topic prepared today. I actually had time to prepare a topic. Hey, Robert, great to see you. Thank you for joining. So nice to see everybody coming in here just to listen to me ramble about the cosmos. I also have a new setup now because the computer that I used to use to broadcast, I had to give back because it was my work computer. So I've got a new setup, new place, new camera angle, new lighting. If there's anything wrong with the setup, let me know. Oh, thank you for the Happs Hug Award. I do appreciate all of your awards. So if the lighting's not great, if the audio's not great, if the Wi-Fi connection isn't great, let me know so that I can try to fix those problems. Not necessarily for today, but for a future stream. And the topic today is not blue dwarfs. As always, blue dwarfs is something I will get to eventually at some point in my life, I think. So, I do have a topic prepared, but just a reminder that this is an interactive stream. The idea here is that you people can ask me anything you want. Any questions you have about the universe, about physics, about what it's like to move country again. Basically, any questions you want, feel free to ask. If you don't ask questions, I get to ramble about my favorite topics. Today, the topic I want to ramble on about is gravitational waves. Now, gravitational waves are one of the coolest things in the universe. They're absolutely incredible. And it's something that I love talking about, and I've been promising for a while that I would do a stream on gravitational waves. And I'm kind of going to cheat because I'm going to use today as a build-up for a future stream. So today I am going to talk about gravitational waves, but I'm going to leave a few cliffhangers that you'll have to come to a future stream to actually learn more about. So, as always, jump in with your questions at any time. Hey, David, great to see you. Thank you for the high award. I do appreciate it. Always great to see you here on my streams. So, what are gravitational waves? So, before we answer the question of gravitational waves, we have to just do a general, basic introduction to Einstein's theory of general relativity. And of course, it sounds like a big, scary concept, but it's actually not. It's very elegant. Mathematically, it's very complex, but there are some key elements that we can extract from there. One important concept in Einstein's GR and Einstein's general relativity is that space and time are not two separate concepts. They're actually intrinsically linked together. You have space and time. You basically have two sides of the same coin. So you can't have space without time. You can't have time without space. You have space-time. Now, what we also know from Einstein's GR is that the gravitational force is basically a curvature of this space-time. Now, one analogy that we like to use that does break down sometimes, but is a good initial analogy. Imagine you have a big sheet or a trampoline, and you put a bowling ball in the middle. What you're going to see is that your sheet is going to bend inwards. This is due to the bowling ball pulling things down. Now, you can make a similar thought process for space-time. If you have space-time and you put a big object with mass, it's going to curve space-time. This curvature will actually cause other objects to move towards it. Again, if you have this sheet, you put the ball in the middle, you let another ball go, it's going to fall towards the first one. It's going to follow the curvature of the sheet, or in our case, the curvature of space-time. One important concept here is that objects will always travel in a straight line on a curved surface. So this is something that is true in all of everything that we know. Objects always tend, especially light, will follow a straight line. Now, when you have a curved surface, this will no longer look like a straight line. So objects will actually move in a curved surface. So one simple way of thinking about Einstein's general relativity, like one of the most simplest ways we can state Einstein's general relativity, is that objects with mass tell space-time how to curve, and space-time tells objects how to move. So that's just a basic introduction. As to just setting the scene here, background of general relativity done in 3 minutes. Obviously, a lot of details missing there. As always, any questions, do let me know. So now we can actually go into the idea of gravitational waves. So what are gravitational waves? If we consider this fabric of space-time that I mentioned before, where we have like space-time merged together into this fabric, gravitational waves are ripples in the fabric of space-time. So they are ripples of space and time itself. So it's not just a wave propagating through space-time, but it is actually a wave in space-time itself. Now imagine you're in a swimming pool with a friend. You grab each other and start dancing around in circles. I'm assuming you're both fully vaccinated and it's COVID safe. You start dancing around in circles. What you would notice in the swimming pool is that there are ripples forming in the water around you, moving away from you. And the same thing happens in space-time. If you have two objects going around each other, they are going to form these ripples in the fabric of space-time that are going to propagate outwards. Now, when we're talking about gravitational waves, like every wave, it is going to have several properties. First, we're going to have an amplitude, we're going to have a frequency, we're going to have a wavelength, and we're going to have a certain speed. These are the basic properties you can give to pretty much any wave. And what we mean by amplitude is the height of the wave. So if you have something moving, I need my slinky toy. My slinky toy is in a box somewhere in a warehouse. But the amplitude of a wave is the height of the wave. The frequency is how often these crests or the troughs of the troughs of the wave pass you by. So you have the mountains and the valleys of a wave, and the frequency just tells you how frequently the mountains pass you by. Then we have the wavelength, which is just the distance between two mountains or two valleys, and we have the speed. Now, one very, very cool thing about gravitational waves is that they actually move at the speed of light. This is something that was a prediction from Einstein's general relativity, and it is now something that we have experimentally confirmed as well. Gravitational waves do actually travel at the speed of light, which is pretty cool. So back to GR here. Oh, fun question. Not sure if I ever asked this before or not, but do gravitational waves dissipate over time? I think you have asked it before, and every time I see this question, I get slightly confused by the answer. Because I would say yes, they do. That's why by the time gravitational waves reach us, they're a lot smaller than when they're produced. They do have this kind of effect where they are dissipated throughout space-time. I'm going to answer yes to that, but that question always makes me hesitate. So for now, let's go with yes. Okay, so gravitational waves were actually predicted already over 100 years ago. Wow, it's over 100 years ago now, definitely. Yeah, time is passing. So Einstein came up with his theory of general relativity in 1915. He made many predictions based on general relativity, such as the way light moves around massive objects, which we've been able to test, the way light gets Doppler shifted throughout the universe, which we've been able to test. One prediction that Einstein made with general relativity was the existence of gravitational waves, these ripples within the fabric of space-time. This is something that Einstein predicted in 1915, part of his general theory of relativity. And Einstein made the comment at the point of, I don't think we'll ever measure these. Gravitational waves are going to be so ridiculously difficult to measure that we're never going to manage. But we have actually managed to measure gravitational waves. And I will never get over how awesome that statement is, that we have measured gravitational waves. It's really, really cool. But I'm getting ahead of myself. So one question we can ask is, what causes gravitational waves? We could answer this from a purely mathematical point of view, but from a more qualitative, easier to understand point of view. Basically, anything that is accelerating within the universe can disrupt space-time and therefore can send ripples throughout the universe. So there are several types of objects. Oh, cool question there from David. Can gravitational waves escape a black hole? If so, could they tell us about the structure in there? I love that question. It's a very, very detailed question there. So, black hole is a region of space-time that is so dense that nothing can escape, not even light. In order to escape a black hole, you would have to travel faster than light in a vacuum. And as far as we know, nothing in the universe travels faster than light in a vacuum. And this holds true for gravitational waves as well. Now, gravitational waves travel at the speed of light, which means if any gravitational waves were produced inside a black hole, they would not be able to escape the gravitational pull of the black hole. However, black holes themselves can produce gravitational waves, and these can actually leave because they're not within the event horizon. This is the whole black hole itself producing gravitational waves. So it's a great question because with the phrasing of can gravitational waves escape a black hole? No, they can't. But can a black hole produce gravitational waves that will travel away from it? Yes, yes. This is exactly where I was going, and thank you for the comment there about conservation of energy. So gravitational waves follow the curvature of space-time. Not directly. Gravitational waves are in space-time itself, so they don't follow the curvature of space-time, other than they follow space-time itself. So if you have space-time that is bent, a gravitational wave will follow this curvature. But a gravitational wave is not an object traveling through space-time. It is a wave of space-time itself. So it is very similar effect to what causes the curvature of space-time. In this case, instead of a curvature, it's a ripple that propagates outwards. So gravitational waves don't really travel through space-time, so they don't follow the same path that particles would follow, for an example, but they are actually ripples of space-time itself. Okay, and this is there. Your first question there about gravitational waves and black holes is exactly where I was heading here. Of what type of object can create gravitational waves? And it's basically anything that accelerates. So some examples we can give, and the most obvious one, which you've probably heard about in the media over the last few years, is when you have two objects orbiting each other. For an example, two neutron stars, which are massive stars that are super dense, but not quite dense enough to be a black hole. They're so dense that you can basically form neutrons in there, which is quite difficult to do. But two neutron stars orbiting around each other will produce gravitational waves. Two black holes orbiting around each other will produce gravitational waves. A black hole and a neutron star orbiting around each other will also produce the gravitational waves. If you have a blue dwarf star orbiting around another star, you will also produce gravitational waves. Anytime you have two objects orbiting around each other, you will produce gravitational waves. And what some of you might be wondering now, the very good question to ask at this point is, if I'm talking about objects orbiting each other, does the system of the sun and the Earth produce gravitational waves? And the answer is yes. When the Earth is orbiting, due to the way the Earth and the sun move around, because the Earth moves around the sun, but it cause a very tiny effect, very tiny wobble on the sun. It's not perceptible, it's meaningless. Jupiter is doing a bigger effect there. But we do actually the Earth does cause a very slight motion of the sun. So in this system of the Earth moving around the sun, there are actually gravitational waves being emitted, but they're so ridiculously tiny that they're insignificant for all intents and purposes. Gravitational waves, in order to be at a range where we could actually detect them in any feasible way, have to be caused by dramatic events, such as two black holes spinning around each other. Now, I don't know what you mean, Scott, and definitely not trolling you. Important to note here that one black hole by itself, not doing anything, will not produce gravitational waves, because it's just by itself, spherical object not doing much will not produce gravitational waves. Tiny in magnitude or wavelengths. Usually when I talk about how small they are, I'm talking about the wavelength. But I will also come to that later as well, in more details. So any two objects orbiting around each other will produce gravitational waves. You can also produce gravitational waves if you have a non-spherical planet, or a moon, or any non-spherical object. For an example, around Mars there is one moon that is very wobbly and doesn't look like a sphere. I think it's Deimos. Does not look like a sphere. It's not spherically shaped. When this moon spins on its axis, it does produce gravitational waves. Basically, if you have an object that looks more like an American football instead of a rest of the world football, and you make it spin, this would produce gravitational waves. By that logic, in any game of rugby, for an example, when they throw their ball around, they are producing gravitational waves, which is kind of cool. Another thing that we think would produce gravitational waves are things like supernova. Now, supernova are these stars that collapse at the end of their lifetime. They collapse and then explode and send a massive explosion throughout the universe, dissipating elements. This process, this explosion in the supernova, is normally not completely symmetrical. It doesn't look the same in every direction, which means it will have a slight imbalance and might produce gravitational waves as well. So these are just some examples of objects, but you can have a lot of other things that produce gravitational waves. And very interestingly, if there's anything dramatic, so if we think about the history of the universe, many billion years ago, the universe was a lot smaller than it is now. So everything was closer together. And there were dramatic processes happening in the universe. I mean, right now, the universe is kind of calm and quiet and not much is going on here. But in the early universe, there was a lot of dramatic stuff happening. For an example, we think there was a period of inflation in which the universe grew exponentially. In a very small amount of time, the universe grew as big, or ridiculously big. This is a period that we call inflation. It was an exponential expansion of the universe. And this would have been such a dramatic process that it actually would have left ripples throughout the whole of space-time. So this is what we would call a gravitational wave background. These would be gravitational waves everywhere in the universe caused by this dramatic process that happened in the universe in its infancy, which is crazy to think about, that it was such a dramatic process that it basically had growing pains and still has stretch marks. And this is something that we can potentially measure one day. Again, I'm getting ahead of myself. It's easy to get carried away with gravitational waves. And another thing that I'm just going to tease you with and not go into details too much, and Scott, to answer your question, yes, any non-spherical object does produce gravitational waves. So that object that looked like a cigar, that asteroid that kind of looked like a cigar, that one would produce gravitational waves. Something else that can produce gravitational waves that I'm just going to tease you with and go into detail in a future stream. Now, we know that the universe has gone through several different phases, several different changes of phase. And when we talk about phase in this sense, we're not really talking like the phases of the moon, or you might go through a phase with blue here and then a phase with green here. And I love phases. But when I'm talking about the early universe phases here, a better way of thinking about it is if you have a glass of water and you boil it, you see that there's a transition from the liquid state to the gas state as you're bubbling the water. Likewise, if you freeze water, you get ice, you have this transition from liquid to solid. And this is what we call a phase transition. Now, the universe in its infancy went through similar phase transitions. Now, it's not necessarily where it changed from liquid to gas or from solid, though I'm not saying the universe was entirely solid, just the properties of the universe changed enough that we can call it a phase transition. And these are things that happened, for an example, when the Higgs boson started giving everything mass. The whole composition of the universe was affected by this. And these processes can also produce gravitational waves. I'm just going to leave that hanging and not elaborate more on that, because I will do a whole stream just about that topic in the future, possibly with guests if I can convince someone to join me. Okay, so gravitational waves, ripples in the fabric of space-time caused by pretty much anything that has acceleration, black holes spinning around each other, neutron star black holes spinning around each other, neutron stars, supernova, rugby balls, weird asteroids that are not spherical. A lot of stuff can produce gravitational waves, but you do need some type of lack of symmetry. For an example, if you spin a pizza base on your finger and you spin it perfectly flat, you will not produce gravitational waves. However, if it wobbles, then you have your gravitational waves. This years ago. Back if you can hear me correctly. Okay. I hope I'm back now. I have a warning saying I have unstable internet. Please let me know if you can hear me and if you can see me. I hope the connection is back and is stable. Well, please just let me know in the comments. Back now, awesome, thank you. I have the issue that I am using a Wi-Fi that is a shared Wi-Fi. And I think if a lot of people are using it at the same time, it's going to have connection issues. Let's see how stable it is now. It says that I'm back to full signal. Okay, in any case, it chose to freeze at a moment where I was just in between conversations anyway, so that's also good. So to recap, gravitational waves are something that Einstein predicted over 100 years ago, back in 1915, and it's something that will cause ripples in the fabric of space-time itself. So what does this look like? What happens if a gravitational wave actually hits you? What does it do? So what happens if a gravitational wave is traveling through you? So now I'm imagining the gravitational wave is going from me directly towards you on the camera here. What would happen is you would grow in one direction and shrink in another, and then you would grow in the opposite direction and shrink. So basically, you would initially get taller and thinner, and then you would get shorter and fatter. So if a gravitational wave is going through, you get smaller in one direction, larger in the other, and then vice versa. Yeah, sometimes I do speak fast. I know that. I've realized I actually speak a lot slower than I did in my initial streams. I found one of my older streams a couple days ago, and I spoke so fast in the early days. I'm talking early days of Periscope, like 5 years, 6 years ago, I was speaking so fast. So I'm much better than I was now, but I know I do sometimes still speak fast. Okay, so what does it look like if a gravitational wave goes through you? Now I want to imagine that we have a grid of points, like you have particles and you arrange them in a circle. So we just have a circle of particles. Hey, Paul, great to see you. I hadn't seen you come in. So nice to see you here. If you sprinkle glitter all around two black holes colliding, would they make a gravitational wave pattern I could see? You know, that is a really, really cool question. So let's just play this thought experiment here. So you have two black holes about to collide, and you sprinkle glitter around them, but far enough away that it's not going to get immediately sucked into the black hole. Now the thing is, the gravitational waves won't actually carry the objects, right? It's not like a leaf that's going to be carried away on the water. The gravitational wave will just pass through the glitter, but it won't actually pick up the glitter to carry it with you. So unfortunately, sprinkling glitter around a black hole, you need a lot of glitter, but sprinkling glitter around a black hole would actually not allow you to see the gravitational waves anymore. Of course, if you're right next to it observing, you might be able to see a small difference, but it wouldn't then carry the glitter. It would actually just change the size of the glitter pieces, and it's not to a way that would be noticeable. You would need very big objects, and even then, it's very, very difficult to see the change by eye. If we could figure out a way to make the tall and thin effect permanent, I'd be on board with that. Yeah, I don't think you can use gravitational waves for that, Scott, I'm afraid. Okay, so I was going to show you here what it looks like if a gravitational wave goes through a ring of particles, a circle of particles. So I have this nice image here, this little illustration. So the red dots represent particles. So here you have a ring of particles, and the blue lines are just showing you what it would look like if we tied this together. So basically you have a spider web on the screen. And what you can see here, again, there's a gravitational wave going directly through the screen. So it's coming from me to you. And what you can see is that the ring of particles gets smaller in one direction and longer in another, and then the opposite effect. So first it gets squashed, then it gets stretched, and the same is true in the other direction. So this is what happens when a gravitational wave is traveling through a ring of particles. Now, of course, the effect here has been greatly exaggerated. Now, the reason I say this is because gravitational waves are ridiculously small. So let's imagine two black holes billions of years ago, so 2 billion years ago, two black holes, about 30 times the mass of the sun, started one of these cosmic dances where they start spiraling around each other and eventually crash. This produces a huge amount of gravitational waves that travel throughout the universe for 2 billion light years and reach you today. Now, this gravitational wave would make you grow by a millionth billionth the width of a human hair. So it would stretch you in one direction by a millionth billionth width of the human hair. Which way was the wave going in the spider web? Left to right, top to bottom, front to back? Right, great question. I should have been more precise with that. So the idea here is the gravitational wave is traveling directly through the screen. So from me to you. So it's as if you have the ring of particles here, and the gravitational wave is going in that direction. You are looking at it front on. So this is the ring of particles here, and the gravitational wave is traveling through it. The ring of particles, gravitational wave coming in this direction, or in the other direction, but it's coming like front and back as you phrased it. So yeah, if a gravitational wave produced by two black holes smashing together was to come through you, you would grow by a millionth billionth the width of a human hair, which is ridiculously tiny. This is such a small effect. Like, how are we ever going to measure such a small thing? And this is why Einstein said 100 years ago, we will never measure this effect. We will never be able to directly measure this. We had already, quite a few years ago, I believe 30 years ago, got an indirect measurement. As I mentioned before, any two objects going around each other will produce these gravitational waves. Now, gravitational waves do have the cool effect that they carry away energy. They carry away energy from the two objects that are spinning around each other. This causes these two objects to get closer and closer and eventually crash into each other. So the energy is carried away in the form of gravitational waves. So one way we've indirectly been able to see gravitational waves in the past is exactly this, with two objects that were spinning around each other, two stars. And we've been able to see that these stars get closer and closer and closer. And this allowed us to calculate, I think my video's frozen again. Let's see. Right, so you have these two stars going around each other. They are releasing gravitational waves and producing gravitational waves, and this causes them to gradually get closer and closer and closer. By looking at how closer these objects get every year, we can calculate the amount of gravitational waves. So this was the first indirect evidence of gravitational waves already, I believe, 40 years ago by now. They did win a Nobel Prize for the indirect discovery of gravitational waves. Sometimes, let's not go on a rant about the Nobel Committee. Let's save that for another day. Okay, so we had seen this indirect evidence of gravitational waves, and I just want to make the comment here, because I hope I haven't worried all of you, because I mentioned before that the Earth-Sun system is producing gravitational waves, and I've just said that this causes objects to get closer. So you might now have the question of, is the Earth actually gradually falling into the Sun because of the gravitational waves emitted? And the answer is yes. The Earth and the Sun are gradually getting closer. But it is such a small effect. Again, the Earth is very, very, very small. The Sun is very, very, very small on cosmic scales. It is such a small effect that you'd have to wait longer than the age of the universe, than the current age of the universe, for the Earth to get 1 meter closer to the Sun due to this effect. So it's not something we need to worry about. We're not going to yeet ourselves into the Sun just yet. I can't believe I just used that expression. We're not going to get flung into the Sun just yet. But we are actually gradually getting closer to the Sun due to this small amount of gravitational waves that we're using. So we're losing gravitation, or we're producing gravitational waves. They carry away some of the energy, and the radius gradually shrinks. So we are actually very, very, very slowly moving closer to the Sun. But it's not likely to be the thing that's going to kill us. The Sun is going to come get us first. The Sun is going to grow, expand, eat the Earth. So we don't need to worry about falling into the Sun due to gravitation, with the gravitational wave effect. It's not due to the gravitational waves. I keep saying that, and just to clarify, it's not the fact that the gravitational waves are being produced that causes this in spiraling. It's a joint effect. You gradually lose radius. The energy is carried away in the form of gravitational waves. The moon is getting further away from the Earth. Yeah, the moon is leaving us. It took one look at the planet, like, I'm getting out of here. Okay, so we've had the indirect detection. But now the question is, how can we actually measure this tiny, tiny, tiny effect of gravitational waves? By now, I hope you all know that we have done this. I know I mentioned it earlier in the stream, but this is not a hypothetical future thing. 5 years ago, 5.5 years ago now, we got the first direct measurement ever of gravitational waves by the LIGO-Virgo collaboration. At the time it was just LIGO, but the LIGO-Virgo collaboration, they measured gravitational waves, and they haven't just done this once by now. They've done it over 30 times, I think 50 times by now. So we have actually measured gravitational waves coming from black holes smashing together, from neutron stars smashing together, and from a black hole and a neutron star smashing together, which is absolutely incredible. So how do we do it? How do we measure gravitational waves here on Earth? We've built amazing experiments that basically use lasers and mirrors. And that's it, just setup of lasers and mirrors. The cleanest mirrors you can imagine, the smoothest, cleanest, most perfect mirrors ever, and a laser with incredible precision. And that's all you need to measure gravitational waves. So the idea here is, again, this is a ripple in the fabric of space-time. It's going to make you grow in one direction, shrink in another. Now, the difficulty in measuring this is even if you had the most precise ruler ever, a gravitational wave would just make this ruler grow and shrink as well. So you can't actually use a physical ruler or any grid mark. You can't like put lines in between your objects and then see how this moves because the whole grid lines would expand as well or contract. So it's really measuring distances within space-time when all of space-time is affected. And this is a profoundly difficult question. Going to have to replay the parts I missed. Okay, the blue dwarfs didn't happen today. Don't worry, Paul, you didn't miss a blue dwarf discussion. Just me throwing out some random comments about blue dwarfs just to tease Scott. You assume the entire compound is perfect level over a few kilometers. Yes. Before we get to that exactly. So how do you actually physically measure them? I mentioned lasers and lasers, mirrors, but we go back to general relativity. One thing we know from Einstein's general relativity is that the speed of light is always, always, always the same in a vacuum. If you make light travel through a different medium, then funny things happen. But in a vacuum, light will always, always, always travel at the same speed. If you travel at the speed of light and you shine a light, that light will still travel away from you at the same speed of light. It's crazy. You know, we're used to the fact that if you have a car and you run behind the car, the velocity between the two of you feels less. But if you're traveling at the speed of light and you turn on the torch, the light from that torch is still going to travel away from you at the speed of light. This is something from general relativity that we know. It's something we can test. So light will always travel at the speed of light. And when we talk about speed, this is distance over time. Now, if you have a laser beam going along a specific path and a gravitational wave comes through and it's going to make the whole distance that the laser needs to travel grow very slightly, but it will still travel at the same speed of light, which means the time it's going to take the laser from one point to another is going to change. So we can use the timing of the laser beams as a stopwatch to measure gravitational waves, which is pretty cool when you think about what we're doing here. If this is not clear, please do ask me any questions because this is a super cool thing. And if it's unclear, let me know because I want you to understand this. This is a cool topic. This is impressive. So if it's not clear, do let me know. Are there new piezoelectric gravitational waves being developed? I'm not actually sure. I honestly don't know what that type of detector is. I will have to get back to you on that. Let me just write that down because that is a cool question and I don't have the answer. So I'm just taking a note of that, Clevon, and I will try to answer you another day on that because that seems like a cool question. So just made a note of that. And I will try to answer. As Scott can tell you, I don't always answer on the same day or frequently, but I will try to answer that question. Are there particles randomly quantum into themselves into and out of existence in a vacuum? Do these show light? So that is a great question there. You can, in the vacuum of space, you can pair produce particles. So you can produce an electron and an anti-electron. You basically borrow energy from the vacuum. You pair produce a particle and an antiparticle, but these immediately annihilate and release their energy back to the vacuum. This process is basically instantaneous. So it does not affect the light beam in any way. And also in order to get those conditions, you would need a perfect vacuum, which is difficult on Earth to produce such a perfect vacuum. But that is a great question. I would be happily discuss pair production more in detail another day. But the overview of pair production, you borrow energy from the vacuum of the universe to produce a particle and an antiparticle, and these immediately annihilate and give back the borrowed energy to the universe. It's a very, very cool procedure. Okay, so we want to use a laser as a stopwatch to measure gravitational waves. So what they do with the LIGO setup, the Ligo Detector is one of the gravitational wave detectors we have here on Earth. They have two arms, each one is 4 kilometers. At the end of each arm, there's a mirror. And at the beginning, there's a laser and a beam splitter. So the laser goes to the beam splitter, it's split in two. The laser light then travels down both legs of the arm, or both arms of the detector, sorry, not both legs of the arm, both arms of the detector, or both legs of the detector. They go down, the laser bounces on the mirror at the end, comes back, rejoins, and is projected onto a separate mirror, onto a separate wall, basically. Now, at this point, we need to consider that light travels as a wave. Every light has its wavelength associated to it. When two waves come together, if they are in perfect phase, so basically if the mountains come together at the same time, you create constructive interference, you get a wave that is bigger. If the valleys come together at the same time, they will create constructive interference, the valleys get bigger. But if the two waves come back out of sync, so the valley of one and the mountain of the other wave is aligned, what you're going to get is destructive interference. The waves are going to cancel each other out. Just to clarify, if you're traveling at light speed, I know it's not possible, but you can, yeah, let's hypothetically travel at light speed and you shine a light, it travels away from you at the speed of light. Yes. Yeah. The photons don't stack up in front of you, the photons do travel away at the speed of light. This is something from general relativity. No matter what you do to light, it will always travel at the speed of light in a vacuum. So you can be traveling at half the speed of light or at the speed of light, let's say, and you shine a light beam, it will travel away from you at the speed of light. Which is also fun because particles of light, photons, don't actually experience time, but that's a whole other conversation. We can't know whether an event is at a right angle to the detector. It must be super hard to interpret the results. Yes. So I will get to how they do that as well. I will get to how they do that. But yeah, light travels away from you at the speed of light. It's just the way light behaves. It's fun. They're not going twice the speed of light. Another observer would measure them traveling at the speed of light. You will measure them traveling at the speed of light. I think I need to do a stream on general relativity because this is a complicated topic that's difficult to visualize. But whenever you measure light, you will always measure it traveling at the speed of light. If you're traveling almost at the speed of light, light is traveling away from you at the speed of light. But another person measuring the same beam of light will also see that it is traveling at the speed of light. It doesn't matter who makes that measurement. Hey, Rev, great to see you. Haven't seen you here in a while. So yeah, maybe at some point, actually in the very early days of Periscope, I did a stream just about general relativity. It took me 3 hours. And it was intense, but it was fun. So we can try to do maybe a slightly shorter version of that at some point and discuss this more in detail. This is actually already special relativity, not really general relativity, but we could do a whole stream of that. But the idea is light always travels away from you at the speed of light. No matter who makes this measurement, you will always measure light traveling at the speed of light. You can tie this together to, if we need the speed of light to be constant, then you have Hall effects like time dilation. So here you would have the thing, you have an outside observer measuring the speed of light, you're measuring the speed of light, but you're traveling at the speed of light. There is going to be some time dilation effects that actually help keep the speed of light constant. So you can use this fact that the speed of light is always constant to pull out time dilation and length contraction. But this is complicated. I know it's a difficult concept. I really do agree with you that it's a difficult concept, but light always travels away from you at the speed of light. Okay, so we have this idea. You can send a laser down 2 different beams. They come back, and you can see if there's constructive or destructive interference. Now, the way LIGO Virgo are set up, they shoot this laser beam down both arms of the detector. It comes back. If all goes to plan, if nothing affects the lasers in any way, when they come back, they're perfectly out of phase, which means they create destructive interference and you get no signal. Now, during this travel time, while the laser beam is going down these arms, back and forth, if anything makes one of the 2 arms stretch or shrink, by the time the laser beams come back, they will no longer be out of phase and you will get a signal. So let's see how this looks. There was actually a cool video of this created by the LIGO Virgo team, just showing exactly what I've explained, but a bit slower. So let's pull up a video here. Okay, so here you have the setup. You see a laser beam goes down, it comes back. This is just the overall setup. Now it's going to go through in a bit more detail. Okay, so we're going to follow a light beam here. You see it has a wavelength. It gets split by the beam splitter. It travels down the arms of the detector, which is a mirror, bounces off, comes back towards us. Now it's going to rejoin with the one that went down the other arm, and they go off to the side to the actual detector. If nothing happens, there's no signal. Now we see what happens if one of the 2 arms changes length due to a gravitational wave. It makes these waves come back slightly out of sync, and then this produces a signal that we will actually measure. So based on whether these laser beams come back in sync or out of sync, we can know if something affected the gravitational wave. Sorry, if a gravitational wave affected the laser beam. So this is a pretty cool setup. We're just using the fact that the speed of light is constant and that we can use constructive or destructive interference. We use lasers and mirrors to detect gravitational waves. And I say quickly, and it will never cease to amaze me that we came up with this incredible way of measuring gravitational waves. It's absolutely amazing when you think about it. You know, I explain it here like, yeah, this is what happens, but it's incredible. I will never get over how incredible it is that humans decided this is how we're going to measure gravitational waves. And it works. It makes complete sense and it works. And we've used this to measure gravitational waves. And that is so cool. So, a few things about this in order to make sure. Now, I mentioned before that these signals are really, really, really small. So, in order to be able to see these signals, you need a very, very good detector that is isolated from other things. For an example, a truck passing by, like a kilometer away from your detector, would produce a bigger signal than gravitational waves. So that's a problem. So the solution they have is there are actually two LIGO detectors, 3,000 kilometers apart. One in Hampstead, I can never remember the names. Anyway, there are two, 3,000 kilometers apart. If you have a gravitational wave signal coming from space, coming from somewhere in the universe, you would see it at both detectors. However, if it's a small truck passing by or a train or somebody bumped a table, that would only be at one of the two detectors. So you have both of them in place to help isolate whether this is a real gravitational wave signal or not. Then there was a comment before by David. Let me just find it again because it was a very good comment. Where's it gone? No, sorry, by Paul. Comment by Paul here. We can't know whether an event is at a right angle to the detector. It must be super hard to interpret the results that might come from any direction. This is completely true. It's very difficult to figure out where they come from. But if you have two of them, you can already kind of start to locate it on the sky of which direction it is. And if you add in a third one, then you can triangulate the signal. Now, this is what they would do in all forensic shows, in all CSI type shows. It's like we're going to triangulate the signal of something. And this is what we can do with gravitational waves. By now, there are at least three. I believe there's actually four now. There's the two LIGO detectors. There's the Virgo detector in Italy. There is one in Japan called Kagura, and there is plans for another detector and another LIGO component to be built in India. But we definitely already have the two LIGO and the Virgo ones, and Kagura joined in September last year. So we have these four, but it's just three of them pick up the signal. You can triangulate and pinpoint exactly where in the sky your gravitational wave signal is coming from, which is really, really cool. Does light disintegrate over time? If you bounce light off of the endless mirrors in space, would it eventually become less visible? So light doesn't disintegrate over time. You send your light beam down, it comes back exactly the same. We're only talking about 4,000 kilometers here, so it's quite quick for the light in any case. So obviously you don't keep it bouncing in an infinite amount of time. At some point you restart the laser. But we don't need to worry about light disintegrating. It has its wave, it will keep its wave, travel back and forth, back and forth. You never even thought about the beam hitting itself on the way back after the mirror and before getting recombination. Yeah, you need to recombine it, but this is a beam splitter is something that you can use in a lot of optics experiments, and it just breaks the light in two. And when then they come back on one side, there's a reflective surface, and on the other it just lets it through. So then the beam in one case is bounced off in the angle you need, and in the other one it travels straight through. So you do need the light beams to come back to themselves. I have seen the question there by Ange about gravitational waves and how many, and I will get to that in a minute. Off topic, but for another time, dark gravity is a term you've heard the other day, dark matter. Okay, dark gravity is something that probably doesn't exist, but we can cover that in another stream. Okay, so, mentioned a few times now. LIGO, Virgo, amazing detectors that use lasers to bounce lasers off of mirrors to measure gravitational waves produced by merging black holes billions of light years away. Absolutely amazing. So this is something that Einstein predicted in 1915 and said, I don't think we're ever going to measure this because how on earth are we going to measure this? And then scientists came up with a way and said, this is how we're going to measure it. So in 2016, we got the first announcement of a gravitational wave detector. February 11th, 2016, there was a press conference by the LIGO team. We'd all heard the rumors, we knew what was coming, and they opened the press conference with, "We did it, we measured gravitational waves." I had chills at that moment. I watched the press conference live, and immediately afterwards I jumped on Periscope. I was jumping up and down. It was so exciting. This is basically like, imagine you've always seen the world in black and white and someone suddenly switches on the color. Like, it's a whole new way of looking at the universe. And it's become cliche, but we have entered the era of gravitational wave astronomy. It is a whole new way of looking at the universe. We don't even know yet the wonders that we are going to discover with gravitational waves, but it just turned on a whole new way of looking at the universe. And I keep waffling on, but I should actually show you what we measured, what LIGO and Virgo measured. This first detection, it is this one here. Some comments here, you mean the individual beam hitting itself while going in opposite directions? Yeah, the way the laser's set up, you don't actually need to worry about it hitting itself. It can still travel. It doesn't create interference with itself. You wish you were still capable of feeling joy like that. Scott, I hope I can transmit some of my joy about gravitational waves to you. I know everyone has a lot going on, but the wonders of the cosmos is something that I hope we can all keep enjoying throughout our lives, because it is amazing. If the gravitational wave is coming through the page, z-axis, why would the two detectors, x and y-axis, take turns expanding, contracting? So you don't necessarily need the two detectors to do different things. You actually want them to do the same. It just depends where the gravitational wave is coming from. Now, if the gravitational wave were coming from directly above the detector, it would be slightly harder. Normally, you want it to come at an angle. Then you get one of the arms and legs contracting slightly differently. So one arm will contract a bit, one would expand a bit, and vice versa. And the two detectors just serve to make sure that you're actually getting a signal from space and not some background noise. There is a slight delay between the two detectors, and measuring the delay will also help you see which direction it came from, where it hit first. So let's see exactly, why would the two detectors take turns? So yeah, it's a thing that they don't take turns. Both detectors do the same thing. And then you reconstruct the form, what we call the waveform of the gravitational wave, at both detectors separately, and then you put it together to compare them. And this is exactly what I'm showing you here. So let me just remove the banner here so that you can actually see this properly. Okay, that should be a bit easier. So now you can see the two gravitational wave detectors. We have the one in Washington and the one in Louisiana, left and right. The top panel shows you the initial signal that came in. So this is the initial reconstructed signal, the red and the blue. In the panel down, in the middle panel, you can actually see several things. In red and blue, there's the reconstructed signal, subtracting some background noise, which is what you see at the bottom. So in the third panel, you have this noise that is subtracted away. And what you can see in grey is one of the predictions for gravitational waveform. Now, we've had over 100 years since Einstein made his prediction to figure out what a gravitational wave signal would actually look like. So we've had plenty of time to run simulations on the computer to see what we would actually expect. So we have a whole catalogue of different possible scenarios as to what to expect if there were a gravitational wave detection. So when these signals came in Washington and Louisiana, they just had to pull up I say it like it's a small feat, they just pulled up the database of all the possible gravitational waveforms we've mapped and found one that fitted. And based on this, they were then able to tell us the properties of the black holes. So what you can see here, detected both by the Washington LIGO detector and the Louisiana LIGO detector, is the gravitational wave detected in September 2015, announced in February 2016. And here you had two massive black holes, not supermassive, two black holes, both about 30 times the mass of the sun. So 1.2 billion years ago, somewhere off in the universe, two black holes came together, one of 30 solar masses, one of like 25 solar masses. They started a cosmic dance, they span around each other, they crashed. This produced gravitational waves that traveled throughout the universe for 1.2 billion years until they reached us here on Earth. And we measured them using a laser bounce back and forth between a mirror. which it's just amazing. I will never get over how cool this is. We have been able to measure black holes merging together billions of light years away. And this is something we've measured. It's amazing. What you can see in the bottom panel is the full reconstruction of what we think the signal looked like. So it's just like kind of this is the some different properties, the frequency, the time. And again, this merger, the actual final signal that we received was less than 1 second. So they had like half a second of signal in the detectors, and they were able to use this half a second of signal to reconstruct what happened. It's amazing. I know this is not the first stream I've done about this topic. I just never get tired of this topic. Now, one cool thing about gravitational waves, they're a wave, they have a frequency, which means we can also make the analogy of what would it, does the frequency mean they were orbiting each other 200 times per second? So the frequency is really the frequency of the gravitational wave that we have measured. Now, in order to calculate exactly how quickly these black holes were merging each other, of course, it wasn't constant because they were gradually getting faster and faster and faster until they hit each other. But then you would have to do the full reconstruction of how far has this traveled and convert the frequency that we're measuring here today to the frequency that actually corresponded to the black hole at the time they were emitted. As we mentioned before, these gravitational waves do dissipate. So the frequency that we measure them here today does not correspond one-to-one to the frequency at which they were emitted. There is some conversion to do. A 30 megabyte-ish black hole, 25 megabyte-ish black hole combined to 55. That's an awesome question, Scott, and the mass does change. So I don't have the exact numbers, but basically in the merger, if you add the masses of the two initial black holes together and you compare it to the mass of the final black hole that came about from this, there is about 3 solar masses difference. And these 3 solar masses of energy, so that's 3 times the mass of the sun, this is the energy that is carried away by the gravitational waves. So you have these two black holes, not supermasses, sorry, these 2 black holes. They were about, let's say, 30 and 30. These are not the exact numbers. And when they came together, they produced a black hole that was around 57 instead of the 60 that you would expect. This is 60 solar masses. The missing 3 solar masses of energy, of mass, were converted into energy and carried away by the gravitational waves. So the gravitational waves themselves are what carry away the energy from the black holes. This is what allows us to study so many properties. This is what allows us to see that the gravitational waves are produced when these objects come together. They come together, but they lose energy in the process. You can imagine they're spinning so fast that energy is basically flying off of them in the form of gravitational waves. So that is a great question, Scott. But the final mass that we received, or the mass of the final black hole is less than the mass of the 2 suns because some energy is carried off by these gravitational waves. Now, because this is a wave, we can also do this analogy of what would this wave be like if it was in an audible spectrum. And this is actually not so far-fetched because the frequency here is kind of one that we can hear. It's a frequency that we're used to. So there is the fun thing you can do of saying, what would this sound like? What would these gravitational waves sound like? And this is not just a crazy question. This is something that we can actually do. And I'm actually going to play the clip next. Let me take away this one for a minute. So I'm going to play a clip and you're going to hear the sound several times. The first 2 times it's the same sound. So I'm going to play the sound of the very first black hole merging. The first 2 times you hear it is in its real frequency, exactly as it was detected. The second 2 chirps that you're going to hear is when we've adjusted the frequency just so that it's more in a range that we're used to hearing, so we can actually change it. So first you'll hear the normal one, then you'll hear the one that's been shifted so that we can hear it. You might have heard several people make the comparison or the statement that we've always only seen the universe and now we get to listen to the universe. This is true. This is exactly what's happened. We've always looked at the universe, and with gravitational waves, we get to listen to the universe. Let me play the clip. I just need to find it. I have so many things uploaded by now. Okay, this one here. Okay, so what you see here is the reconstructed waveform shown on the screen with the symbol that looked like a bat symbol that we had before. And you can hear the chirp produced by gravitational waves. So what we just listened to is the after effect of two black holes smashing together somewhere in the universe 1.25 billion years ago. And now we can hear this chirp, this chirping noise that shows us what happened, that tells us about the universe. This is incredible when you think about it. We've always looked at the universe using the electromagnetic force, and now we can actually use gravitational waves. It's a whole new way of measuring stuff in the universe. I'm talking about this one, the first one that was done, the one that was announced in 2016. It was big, it was a huge discovery. It's absolutely amazing. Oh, lots of comments, just missed some comments here. It is incredible, thank you. I'm glad you share the enthusiasm with me there. The visual simulations always show waves propagating two-dimensionally along the plane they're orbiting each other on. That is a great question, Scott. So if you have two black holes orbiting in this direction, the waves are produced along that direction. So they're not spherical waves. They do have a direction of travel, so it will be along the plane that they're orbiting due to conservation of angular momentum. Okay, so I've shown you this one. This was the first time it was done. This was amazing. The first ever gravitational wave detection. We measured it here on Earth. We can listen to it. But this was in 2016. LIGO, Virgo, and now Kagura have been running since then. So, a lot has happened since then. We have not just measured two black holes colliding. We have now been able to measure two black holes coming together, two neutron stars coming together, the really cool thing of a neutron star and a black hole smashing together. A lot of amazing things. So there was the question before by Ange that I wanted to get back to of how many events have we measured by now? So let me show you the current catalogue. This is the current catalogue of all gravitational wave events measured and the reconstructed black holes. We have had 50 measurements. You can actually get notifications. There's a Twitter bot that will ping you anytime there's a new one. We have now had 50 detections. This is in the last 5 years, since 2016 when the first one was announced. We have had 50 of them. So what you can see here is the different events. I'm not sure how well you can see because it's pretty small. The blue ones are the black holes that have been measured by LIGO and Virgo. And you can always see that there are two small black holes that go together to form another one. On the vertical axis, you can see the mass in solar masses. So one solar mass would be at the bottom. At the top, you see 160 solar masses. So every dot here corresponds to two black holes going together to form one. You can see the arrows that point them upwards. Then there are the purple ones in the middle, which are not ones that have been measured via LIGO and Virgo. These are the electromagnetic ones, so ones that have been measured in other ways. And you can see there's a lot fewer. Then in yellow, you can see the electromagnetic neutron stars. So these are neutron stars that have been measured with other ways, other mechanisms. And in orange, you can see the LIGO Virgo neutron stars. So the neutron stars we have measured from LIGO Virgo. Again, you can always find two orange ones that go together to produce another one. And there is a very cool one. Let me just make it full screen to make sure you can see this. This is absolutely amazing. We have 50 of these events. And somewhere in the middle, you should see there is a combination of one orange one and one blue one. So we have actually been able to measure a neutron star and a black hole coming together, which is absolutely amazing when you think about it. So yeah, 100 years ago, Einstein came up with a theory to help us understand the universe. A prediction of general relativity was gravitational waves, these ripples in the fabric of space-time carried away. So ripples in the fabric of space-time caused by dramatic events carried away throughout the universe, carrying energy with them. In 2016, there was the announcement that for the first time ever, humans had measured gravitational waves. We'd actually been able to listen to the after effects of two black holes crashing together. And in the last 5 years, we've been able to do this 50 times. We've measured 50 different events of gravitational waves caused by objects smashing together in the universe. Now, once you reach 50, you can also start doing statistics. It is no longer just one. You can now use this to ask questions about what are black holes like? What are the average masses of black holes? How do they behave? The same for neutron stars. We can start asking questions because now it's not just one event or two events. We now have enough to be statistically significant, which is amazing. LIGO is still running, Virgo is still running, Kagura is still running. We have more and more of these events expected to come. We've got 50 on. Again, this is just the beginning. So it's become a cliche thing that every paper that mentions gravitational waves will include the sentence of a new era of astronomy. And it's become a cliche, but it is true. We have a whole new way of looking at the universe. And I hope I've convinced you that this is absolutely amazing. Does the gravitational wave point to locations? They do. Only if you can have at least two, potentially three measurements, because then you can triangulate the signal. And now we have the two LIGO detectors, the Virgo one in Italy, so two LIGO ones in the US, Virgo in Italy, Kagura in Japan. There's more expected to come on. And with them, you can actually triangulate. With the first ones, with just LIGO, it was like it's in this general band of the sky. But now with the three of them, you can actually point to an area in the sky and say, up there, in that direction, this many billion years ago, two black holes crashed together, and this is what we measured today. This is what we heard today because of that. So you can actually triangulate the position. Does the location of these gravitational wave detections benefit in certain areas over others? I'm not actually sure. I'm not sure where they're distributed in the sky. I think you can actually find a map showing where they're distributed in the sky, but I don't have that at hand. But that is something that people are working on as well. What does this tell us? Why are there more black holes in one direction than another? But I don't have that map at hand, so I can't speculate about that. But yeah, once you have the map with more data points, then you can start doing more statistical analysis, which is fun. So gravitational waves are amazing. I hope I convinced you of that. But I did mention at the start of the stream that this was just going to be a cliffhanger to hype up another stream. So I think these gravitational waves are amazing. These ones produced by black holes smashing together. Black holes of around the solar mass, like 30 times the solar mass, smashing together is pretty cool. But this is just the beginning. These are gravitational waves at one specific frequency. But we know there should be gravitational waves at a lot of different frequencies. I hinted before that you could even have these gravitational waves caused by things happening in the early universe, the universe being so dramatic, changing so much that it produces gravitational waves that are left as a background radiation everywhere in the universe. So I just want to show you another image here. Cool question here. Could you have two blobs of dark matter merging and creating gravitational waves? Absolutely. You would, in order to actually be able to see them, you would hope that they are very big blobs of dark matter, because if you just have a blob, a handful of dark matter and a handful of dark matter here, and they merge together, they will produce gravitational waves, but you're never going to be able to see them. If you think that in order to see these from LIGO Virgo, we're talking about black holes that are 30 times the mass of the sun at least, you'd need pretty big clumps of dark matter. And we have very good limits on how big dark matter can grow. So we don't expect that they are planet-sized chunks of dark matter just floating around, because if that were, or like black hole-sized chunks of dark matter, or stellar star-sized chunks of dark matter, because if this were the case, you already would have seen them in certain experiments. So it is a great question. Hypothetically, if you had two massive black holes, two massive clumps of dark matter that crash together, you could produce gravitational waves. There's a whole other story we can go into there that I don't have time to do today. That there is a possibility that some of these black holes that LIGO has detected are actually made up of dark matter. So we could have primordial black holes. So all the ones I've talked about today are stellar black holes. So a star reaches the end of its lifetime, it collapses to form a black hole. But there's another type of black hole known as primordial black hole, and these would have been produced in the early universe, where space-time itself collapses to form a primordial black hole. And these primordial black holes, we're not completely sure on their properties. Some people think that these primordial black holes are actually the black holes that LIGO and Virgo are detecting today, based on some properties. And this is a hot topic. Like every week, there's a new paper saying LIGO measured primordial black holes and therefore dark matter. And the next week, there's a paper saying no, because. So that's a whole other story, but It could be that LIGO Virgo have actually already measured a small component of the dark matter. I should give my streams clickbaity names like you won't believe what we've measured. Yeah, I could start doing that actually. Okay, so I've been hinting at this, and now I want to show you. You might all have an image in mind of the electromagnetic spectrum, blue on one end, red on another, a wavelength in between, and some nice badges like here is radio astronomy, here are gamma rays, here's microwave. So why don't we do the same for gravitational waves? And let me show you this image here. This is going to be a teaser image. So what you can see here is the different types of gravitational waves. At the bottom, you can see the detectors. At the top, you can see the possible sources. Now you see this covers a range of frequencies shown in the middle. At the top, in red, we talk about quantum fluctuations in the early universe. And the arrow shows you across all possible frequencies that this could be produced. Now, this would just be the real side effects of this early period of inflation in the universe. The background radiation, instead of the cosmic microwave background radiation that we're all used to, this would actually be the gravitational wave background radiation. And there is a CMB on the screen. I hope you've all noticed that. The next arrow you can see in green is binary supermassive black holes. So today I've been talking about stellar mass black holes, but now imagine if these mergers instead were produced by supermassive black holes. Amazing. Also something that would produce gravitational waves. In blue, you can see compact binaries in our galaxy and beyond. This is basically what I've been discussing today. In red, you can see rotating neutron stars, supernovae. I mentioned briefly that an exploding supernova would produce gravitational waves. Then you can see another green arrow here of compact objects captured by supermassive black holes. So now the question is, what if you have a neutron star smashing into a supermassive black hole? So you can see all of the possible ranges of frequencies that can be produced for gravitational waves. Now, if we go down to the panel of detectors, on the right-hand side, you can see here we have the terrestrial detectors, LIGO, Virgo, Kagra. These are the ones I've been discussing today. On the left, you have the CMB, the polarization of the CMB. We can actually use the CMB to constrain how many gravitational waves were produced in the very early universe. Super cool. Not going to go in detail, but super cool. And you get the CMB picture. Second from left, you have the pulsar timing array. This is looking at specific type of stars and basically using these stars as a stopwatch. You can do this and measure different gravitational wave frequencies. This is where the nanograv result lies, which I'm not going to discuss today, but they have found something. And then there's a region you see here colored in green, the space interferometers. Now, the idea here is, okay, LIGO Virgo is awesome, but what would happen if we sent something like that to space? And this is not just a crazy what if scenario, this is actually something that is planned. There is an upcoming space-based gravitational wave mission known as LISA, which is going to be 3 small telescopes in a perfect triangle chasing the Earth. So they're going to be rotating, following the Earth's motion around the sun, a couple of million kilometers apart, at an incredible precision, measuring basically a laser going back and forth between them. Not an actual physical laser, but that's basically the operation principle. So we've decided building this amazing detector on Earth is not enough. Let's send one to space. How cool is that? So I've mentioned a few times in the past, some of you might have heard me mention over the last few months, that I've had a topic change with my new job. I was going to change topic. So up till now, my focus has always been on CMB and dark matter. Now I am actually moving into gravitational wave physics. As you might have gathered, I'm kind of excited about this. And I will be investigating things like what can we hope to do with LISA. So this space-based gravitational wave mission that can tell us about a whole different amount of things in the universe. This is what I'm going to be working with now. So that's why I did this topic today. And I said I was going to leave a lot of things hanging because, of course, there needs to be a stream all about LISA, about the LISA detector. I also need to do a stream about pulsar timing array and the nanograv result. So this is just to show you that everything we've discussed today, which is amazing and awesome, it's just the rightmost panel of this figure. Everything else is still pending. So I hope I've got you excited also about my future streams because this is really, really cool. But yeah, I will still be working on some projects on dark matter and CMB as well because I can't walk away from those. But this is where my focus is going to lie. That also means that I've now joined a group of experts on these topics. So let's see who I can get to join me in future streams and what fun topics we can discuss. Where is the gravitational wave mug? You know, that is a great question. I have a CMB mug, which is somewhere in a warehouse. I was given a mug of the Helsinki University. I was so happy. My first day in the office, they gave me a mug. It's like the easiest way to make me happy is give me a mug that has some type of symbolism, not like I found a random mug in the shop, but a mug that has symbolism to me, and I will be super happy. Anyway, on my first day in my new job, I got a mug with the Helsinki University logo printed on it. I love it. I'm so happy. Okay, so I went a bit over the 1 hour, but I was talking about gravitational waves, so I expected to go a bit over time. I hope I've convinced you that gravitational waves are amazing, and I hope I've convinced you that we've only just began to do gravitational wave physics. There's so much more to do. Going forward, you can expect a lot more gravitational waves on my streams, hopefully with experts. And in about 10 years, when LISA launches, in 2034 is the scheduled launch, I am going to be so stressed. There's so much riding on that mission. I'm already stressed about it, and it's like 12 years, 13 years into the future if there's no delays. But it will be really, really cool. Okay, thank you everyone for the nice comments. Thank you, Scott. Thank you, Paul. To everybody who's joined in with questions and comments, it's always great to have you here. Always great to see you. I hope you enjoyed this topic. I prepared it this morning, and actually, you have Ange to thank for this topic. Because yesterday I was saying I'm not sure what I'm going to talk about. She said maybe gravitational waves. Like, yeah, you know what, gravitational waves. So yeah, it was a cool topic. I'm glad I did this today. So I should be online next. There's a behavioral experiment that involves giving people mugs. You know, I don't care if I'm part of an experiment if I get a mug. I like mugs, and I got my mug, and I'm happy about this mug because everyone. It seems like a lot of people in the group have one, but mine has a minor defect in one of the printings, which means mine is unique. So I like it even more. Thank you for the Super Heart Award, David. I do appreciate all of your awards. They do mean a lot to me. And the fact that you will just choose to spend a part of your Sunday here listening to me ramble about the cosmos. I love that there's so many of you here. I should be online again next Sunday. Now, depending on how things go during the week, next Sunday I might be discussing a new paper that I'm putting out, hopefully this week, depending on how things go. I'm not going to give any details, just depending on how things go. Next week will either be a random topic or talking about a paper that's going to be online in the next few days. We'll see. We'll see how things go. But in any case, I should be online again next Sunday. Maybe during the week, I'll try to do another sunset stream because I have very nice views from here. It's already dark here. But on times when I can catch the sunset, I will maybe try to do one of those again. So I hope to see you all again very soon, probably next Sunday. And in the meantime, I hope you all stay safe and take care of each other.